Okay, today, got a couple of things. Tyler, question first?
What section is this in the book?
It's going to be chapter 3, section 3 and 4, I believe. 3.3, 3.4. What I'd like to do today is first, before we get going on the material, new material, is mention to you that we have a first midterm, and we'll do that over in the computer lab tomorrow from 10 to 12. And I'm designing it as about a 1 hour kind of math test on the material you've already seen, up through 3.2, which is the linear modeling stuff that we worked on yesterday, okay? And I probably won't do any data modeling problems with you, but I do expect you to understand concept of slope, x-intercept, y-intercept of straight lines, perpendicular lines, parallel lines, the fundamentals, which essentially is from beginning algebra. You need to know that, plus the other material we'd covered prior to this material in 3.1, 3.2. And what I suggest for studying is the old homework quizzes that you've done, and that 20-point quiz you did, and then the other kinds of homework problems that you've been working on that were hopefully in your notebook. Okay? So I'll design it as a 1 hour type of event, but I'm going to have you in the lab, and you'll all do the problems, show your work on scratch paper, turn that scratch paper into me when you're done, and you'll key your answers in MathXL. Okay? That way you'll get the immediate feedback, and then I'll be able to look at your work that you've written out step by step, and then I can give you back partial credit occasionally if there's something where you keyed it in wrong or something like that. Okay? And Max, I'll talk to you right after class, okay? Then also, there's that CRN 23098. Some of you, I'm giving 10 bonus points, and some of you have done that. Tomorrow's the last day that you can do that sign up. So check in with me tomorrow if you've done that. I've got some of you, I've already written down that 10 points. The rest of you, please do that so that we can get that one in the bank, and then that helps support our tutors over in the Resource Center. Okay, now for the material today, what we did yesterday is we reviewed linear function behavior. And then we built a scatter diagram from some real data and went ahead and generated the line of best fit using what's called a regression function out of the calculator. So what I want to do is something similar to that, similar to what we did yesterday, except this time we want to take data that looks more like a parabola in the way that it scatters itself out. And I think it would be really good for us to go completely through the fundamentals of quadratic functions, which you have been exposed to previously, but I want to make sure we go through all of those basics with you to refresh your memory. And part of that would be the quadratic formula that you've all seen before, but how many of you have forgotten it? Quadratic formula, forgotten it. Raise your hand. A few hands going up. Okay, I bet more of you have forgotten it than was just indicated. I want to go through completing the square, which is really useful to us because this helps us determine where the parabola sits if we actually have a quadratic function and we want to draw its sketch. And we can then, once we have the square completed, we can identify where the vertex is and easily find the zeros. And then we'll address, we keep coming back to these kind of things, these fundamental properties of functions, and we'll go ahead and look at that. And then we'll also then look at a data set and generate a regression function. Okay? So we'll look at a data set and then generate a regression curve. Like we did yesterday, except this time it'll be looking like a parabola. All right, ready to start? Any questions? Okay. Let me take a problem. I gave you folks a handout. And I think what would be useful is to, I can use that problem that I gave the handout, and that way you don't have to take notes on it. But let me just hit a couple of the basics with you first. You need to make sure that you have this in your head. And I've said this several times already. Graphically, it's called our squaring function. Its end behavior, how would you describe end behavior? If somebody else in college algebra came up to you and asked, tell me what the end behavior of this thing is. How would you describe that?
Up, left, and upright.
Up, left, and upright. If you go way off to the left for large negative x values, the y values here are growing. So I think they're doing some construction somewhere, so that's what that buzz is. Yes?
So you can describe the end behavior as a positive parabola starting with a vertex at the origin?
No, the end behavior is large values in the domain to the left and to the right. So what's the function doing if x becomes large, either positively or large negatively? Okay? So the way I like to describe it, the textbooks don't do that, but it's got up left behavior and up right. There is a more sophisticated way of showing that. Over here, if x goes towards infinity, y is approaching plus infinity. See that? And over here, for up left, if x is approaching negative infinity, y is approaching what? Positive infinity. And by having the graph, you can easily see that stuff. You can easily see that. And a quick and dirty way of saying it is up, left, up, right. Pretty easy. So, if you ever see a function that has a quadratic character in it, then that means it's going to be behaving something like this thing. So now, let's take something real basic, just to review something that makes everybody stay in the comfort zone. Let's say we had x squared minus 5x plus 4. Pretty basic parabola. Now, what's the behavior of this function? Doesn't it have x squared character? So it's going to behave like x squared. Now, what does negative 5x plus 4 do to it? Any ideas? Or are you just waiting for me to tell you? Plus 4 is going to lift the whole graph up 4, right? And then this does something strange to it, doesn't it? So this is going to do some alteration, but nevertheless, the shape or the character of it is still going to look like a parabola, x squared. That's what you want to observe. This is called the leading term. The leading term. And it sort of helps you understand the general character of what to expect when you get the picture. Okay? Now, what did you do back in your basic algebra background with something like this? Factor. If possible, you try to break this thing into a pair of multipliers, right? So factoring is sometimes useful. So in this case, we can factor this quadratic function, and you should be familiar with that. When you see a negative in the middle, and you see a positive over here, the only way that thing will factor is if there is a negative in the binomial there and there. That's the way you're going to get that last term being positive. Then you typically look at the factors of this 4, which make up that value, and it looks like, without me going back and teaching the beginning algebra stuff here, it's going to turn out to be -1 and -4 to give you your positive 4 last term. Your front end term, you know, is this x and x for your leading term x squared. And you can see the inside and the outside pairs combined together, -x and -4x to get the middle -5x. Why is the factored form real handy if you can get it? Everybody hear what she said? You can get the zeros of this polynomial. You can see the zeros by looking at this factored form. So when you let y equal to 0, you're then thinking of solving the equation x minus 1 times x minus 4 equals 0, and this is something times something equaling 0. That could occur if x minus 1 was 0, or if x minus 4 was 0, and x equals 4, and x equals 1. And you should know, what does this do to the graph? What's this information useful for on the graph? It's the zeros, right? The zeros, because y equals 0 at these x locations, that's where your y value is 0. So with that information in mind, from your background, you know that we have a 0 at 1 and at negative 4. I'm sorry, positive 4. Here and here. We know that the end behavior is, looking at the leading term, up left and up right. Up left, up to the left, and up to the right by noticing the leading term. So this graph we know is going to be going up left in its behavior and up right. Notice the way I'm drawing those little arrows. They're getting steeper. They're not turning over this way. That is important with polynomials. The end behavior will always sweep upward, not turn over like it's coming in for a landing. Important. Okay. So, sketch. Can I put any more detail on here besides these two zeros and the up, left, up, right behavior? The Y-intercept. Polynomials are really easy to find Y-intercepts. You just drop in x equals 0, right? Disappears, disappears, you're left with 4. So when x is 0, y is 4. I changed my scale there so I can make it fit, okay? Okay? And then you know also that parabolas have, what's down the middle? Symmetry. There's an axis of symmetry, isn't there? An axis of symmetry to parabolas. So we know then that halfway between 1 and 4, how do you find the midpoint? First week of the course, add them together and divide by 2. 5 halves, right? 5 halves is 2.5, isn't it? So right there at x equals 5 halves is where the vertex is going to sit. And we know, since it's up left and up right behavior, that it's going to come down in a nice smooth arcing fashion and bottom out symmetrically, sweep then up to the right. Okay, now that's all review, isn't it? Everybody okay? Okay, we want to make sure you still know that, just like we wanted you to know that linear function stuff that we reviewed yesterday. Okay, very easy. It was easy because we could factor it. Now, what I'd like to do, though, is come back to this general form here, the original form. This original form, and let's complete the square so we can easily see how to find that vertex. And the zeros as well. Okay, so we know we have a vertex here at 5 halves, but I don't know how low it goes yet, do I? Okay. Let's come back here now and practice completing the square. How many of you do not remember how to complete the square? The majority. Okay, that's what I thought. So here's what we do. And I believe I reviewed that a couple weeks ago. But not very much stuff stays in your head until you hear it over and over and actually sit there and do it. So here's how we do it. I think I want to try to fit it on this board just for the detail. And so here's how you do it. X squared minus 5x plus 4. We have a coefficient on the quadratic term of 1. We need to have that set up that way to be able to complete the square. And I'm going to do a more complicated one in a couple minutes with you. Now, over here we have negative 5. So what we do is, let me erase this portion of this graph just so I have a little more room. Y equals x squared minus 5x. I leave some space and I keep my plus 4 out there, leaving a little space. I take this linear term's coefficient, which is negative 5, and I want half of it, 5 halves. I suggested this technique to you a week or so ago. You take and write down half of the linear term's coefficient and circle it. You then do what? Anybody remember? Square it, which is 25 over 4. And we tuck it in right here, 25/4. And then we just took our equation, this function here, and we just jacked it up by 25/4, didn't we? So it's not the same as the original. So what we need to do is either add 25/4 on the left side to keep this balanced, or on the tail end here, or subtract off 25/4. So what I want to do is I just want to keep all this stuff over here. So I'm going to put a subtracting 25/4 off the tail end of that. All right? As I suggested in a previous class session when we reviewed this technique, is I suggested you could take a break now. Okay? And then come back. You could turn the DVD off if you're watching the DVD. Come back a few minutes later and go ahead and keep on going, because we've written this number down right here. We have created right here, by tucking this square of this coefficient, half of this coefficient in here, we have forced this trinomial up front now to be a binomial square. If you're watching the DVD, you can repeat that sentence over again. This is a binomial square, and it is x minus 5 halves quantity squared. Those first 3 terms turn into this. Okay? Don't forget, off the tail end there, we still have 4 minus 25/4. All right? But now we need to get the 4. We need to take 25/4 away from 4. So the best way to do that is to get a common denominator, which happens to be a 4 here. So we need to hit this top and bottom here with a 4. So we have 16 less 25 is negative 9. And so finally, we get this thing in a form that's going to be very useful to us. When you combine this, 16 less 25 is minus 9/4. This is really handy, this format. Why is this handy? Look at the picture. What do you see happen to your fundamental parabola? Shifted from the symmetry to the right by 5 halves. Do you see it right there? Shifted to the right 5 halves. And look at that. This is not just a bunch of gibberish here. Okay, this thing is useful, isn't it? What did it do to the parabola? It took that parabola, slid that parabola 5/2 to the right and dropped it 9/4 down. So that's a pretty handy feature, is to be able to complete the square on a general form of a quadratic function, to put it in this format so that you can identify the combination of the horizontal and vertical shifts. Yes?
Would you suggest completing the square before you do factoring so you have more
Yeah.
information?
Yeah. Now this problem happened to have been factorable. I deliberately made it that way because I wanted to take us back to something that's actually almost back in your beginning algebra background that makes you feel comfortable. Okay? But this is a much more powerful approach, and this can always be done with quadratic functions, is completing the square process, always. Okay. So now, what if the question had been, over what interval is this original function decreasing? Over what interval is this, if that was the only question being asked, over what interval is this quadratic function up here decreasing? You would do this work, draw the sketch, and then it's sitting right here in front of you, isn't it? Decreasing from negative infinity on the left, coming over to 5/2, but not including the 5/2 because it's not decreasing or increasing there. Carmen?
Couldn't you just do negative 2a?
Oh yeah, yeah, that's another way of looking at it. Yeah. Okay. So you see how being able to do this process is going to be very useful for answering. Here's one example of the kind of question that could be asked. Another question that could easily be asked is simply, here's your function, where's the vertex? If you take a couple minutes and complete the square, you immediately can tell where the vertex is. So these are all different kinds of little questions that could be asked about a general quadratic function given to you. Comfortable? Everybody feeling good with this? Okay. Now watch something else. If you've done the work to complete the square, what if the question was, what are the zeros? And let's say you did not know that that original thing was factorable. Let's say you didn't see that it was factorable like we did earlier. So if you did this work and got it down to here, how could you find these zeros? What do you do to find zeros? Everybody agree with what she said? Set y, excuse me, set y equal to 0, right? So let's take this equation and set y equal to 0. Now keep in mind, I'm not just doing it because of this simple example. I'm doing this so that you have a general approach to how you can explore these things. So if we set y equal to 0, can I tuck it in on this board, or is it getting too messy? How about right in here? Let's do that. Let's try to tuck it in right here. Let's let y equal to 0. So we have a binomial square minus 9/4 equals 0. Right here. Feel good? The unknown x that we're looking for is tucked inside this square, isn't it? So suggestions from somebody in the middle row or two? Move the 9/4 to the other side. In other words, isolate this expression that has our unknown. And that's usually a good strategy in math, is isolate the unknown as much as you can. And then, as you just said, square root both sides, because that releases this x then. It gets it out from underneath that square root if you square root both sides. So you get x minus 5/2 equals plus or minus square root of this, square root, not square, 3/2. And then you move the 9/2 over to the other side. I'm sorry, the 5/2 to the other side. And you get, look at the two answers you get coming out the door here. 8/2 is, you guys awake? Okay, 8/2 is 4. And the other one, 2/2 is 1. So we get the zeros, 4, 0, and 1, 0, as we did earlier. Okay, so if you've taken the time to complete the square on a quadratic function, then the zeros are really easy to find by taking that result and putting that y equal to 0, isolate the quadratic term, solve for that x, as we just did here. You all
Especially easy if that happens to be a perfect square, that fraction would be it.
This will always be a perfect square here.
The other part won't be.
Well, sometimes that's going to be an irrational number. It's going to have a radical in it that you can't get rid of, like maybe square root of 11 or something like that. All right? Is this all review for you? It should be review. You should practice some of these, which I believe are in assigned homework, to make sure that you can do this as well as I can do it. Okay? All right. Let's now take a little more complicated example. And then after I've done one more algebra problem with you, then we'll go to something that's real with some data and actually do the data modeling. Okay? Any questions on this stuff first? I want to make sure you feel good about this. Okay. So for those, I passed out this, and there's an extra copy up here for those who maybe missed class in the last day or so. It's a general quadratic function, and I mentioned I call this the world's best way to complete the square, according to me. Okay. And so here's the problem that we will tackle. And if you have the handout, you don't need to write the notes down. Here's a new problem. Y equals 3x squared minus 5x minus 7. So what I would suggest you do on these is the following. And what I'm going to try to do is I'm going to try to tuck all this work in right here on the left side, because I want to do a general problem with you right over here. So I want to parallel this using A, B, C that you've seen before, right? AX squared plus BX plus C, right? You've seen that thing a lot. So I want to use the structure here, complete the square on this using the numbers, and then what we'll do is we'll go over there and generalize it in a few minutes. First step, we need to make this just a plain old x squared. I've got trouble because I have a 3 hanging here. Now, what I want to, there's a couple ways I could do this. How could I kind of I shouldn't say disappear the 3, but what could I do to make this into 1x squared here? I could divide both sides by 3, couldn't I? Divide both sides by 3. Okay. Let's do it that way. The other, here's the reason I was tempted to do something else here, or pausing, is I could take this and factor this 3 out right here. How did I do it on the notes? Did I divide by 3? Okay, let me do it the other way since you already have that on paper. Watch this. If I factor this 3 out of here, minus, I don't have a factor of 3 and 5. couldn't I tuck a multiple of 3 in there as long as I put a division by 3 also in there? You agree? Couldn't I tuck in a 3, what's the last number, 7? Minus 7? Okay, couldn't I tuck in a 3 multiplier there just because I want to get a 3 in there? As long as I tucked a 3 underneath there? Isn't that 15 over 3, which is still 5? Okay, we could do that. And now grab this common factor of 3 and pull it out front. So I'd be left with x squared minus 5/3 x, leave some space, minus 7. Everybody agree this is still the same as the original? Okay. Now, we want to complete the square on this thing. So what do we do? Yeah, so don't we take half of this thing? Half of negative 5/3 is negative 5/6 that I suggest you write down right there, right? Square it. 25/36, right? Tuck it in here. 25/36. I can't just go tossing in an addition of 25/36 times 3 into that, can I? Because it unbalances this. It doesn't keep it balanced left and right. So, off the tail end over here, I've added what? Be careful here. I've added actually 3 times 25 over 36, haven't I, to the right side? So I need to subtract off that 3 times 25/6, 36th, right? And you go, boy, this is getting pretty messy. But it's just arithmetic, isn't it? But we all oftentimes have trouble with it. Everybody feel good? Okay. And so now, there's about 3 or 4 of you that have been speaking up. I'd like to hear from some of the rest of you. So those who've been, there's about 3 or 4 who've spoken, so you guys be quiet. Let me hear from somebody else. Next step. Help me. 3 times x minus 5/6. Good. Quantity squared, right? Because this thing traps now as a binomial square using that number. Isn't this nice writing that down and circling it? Because we reuse it right here, don't we? And then we have some arithmetic to do over here. Minus 7, and then 3 goes down into 36 12 times, doesn't it? 12 times there. So we have minus 7 minus 25 over 12. And then we need to tidy that up with a common denominator of 12, don't we? And what's 12 times 7? 84? So negative 84 minus 25 more 12ths, right? And so that's 109 minus 109 12ths. And up front we have this. Get this. Does this agree with what's on your paper? 109 12ths? Now the question is 109 divisible by any factors of 12? It's not even, so 2 doesn't work. Does a 3 work? No, 3 doesn't work. Okay, so I think that's reduced. So, vertex, folks? Where's the vertex of this parabola? Excuse me? Careful. Which way is this thing shifted? To the positive 5/6. Comma. And then down 109 12ths. There's your vertex. Now I ran out of space because I want to leave some space over there, but what I want to do is come back over onto this board. I think I can erase this guy, this more elementary example. And I want to do one more thing with you with this form. And we'll get to the sketch in a second. I want to find the zeros. Are there any zeros, folks? Think about this graph. You look at the original, and it's an upward opening parabola, isn't it? So you know it's in behavior, up, left, up, right, from the original term, 3x squared. But what's that 3 do to it? What are you doing to the y values on x squared? Aren't you multiplying them by 3? Multiplying them by 3, so that's going to kind of stretch it vertically, make it tall and skinny, and then shift it to the right and down. So how many zeros will this thing have? 2 zeros, right? Think about where this thing goes. Tall and skinny, up, left, and up, right. Over and down is going to have 2 zeros, isn't it? So let's set y equal to 0 real quickly here. And so y equals 0. We're looking for the zeros. And we have 3x minus 5, 6 quantity squared. I'm going to take that 109/12 and kick it to the other side, right? Because I've set y equal to 0. So it's going to equal the 109/12. Multiply both sides by 1/3 to get this 3 out of here. Instead of dividing by 3, isn't it easier to multiply by the reciprocal of a 3, which is 1/3? And then you can see I get 109/36, and that's equal to the isolated binomial. Same process as we did earlier, except the numbers are just a little messier. And so x minus 5 sixths equals plus or minus square root of 109 square root of 36, you know, is 6. Move the 5 sixths over to the other side, and we get our answer. 5 sixths plus or minus the square root of 109 over 6. 2 zeros. Yes?
So do you want us to kind of simplify that and make it 5 plus or minus 1, the square root of 109 all over 6?
That's the way you oftentimes have written it in the past. And what I wanted to do is I deliberately wrote it this way for a reason. Because you can see clearly that if you go to x equals 5 sixths, if this is 1, if you go to 5 sixths, here's where the line of symmetry sits. At 5 sixths, if that's 1, your vertex is going to be down here somewhere. At 5 sixths, and how low? Look back at the earlier work. Negative 109/12. And then what I wanted to do, the reason I did it separately here is, folks, is I want you to see the numeric symmetry. By going to x equals 5 sixths, and then you're going to move to the right radical 109 over 6. This is a little bigger than 10 sixths, isn't it? 10 sixths, roughly, a little bigger than 10 sixths. So it's going to kick over here somewhere. See, somebody, if you punch that radical 109 over 6, roughly a little bigger than 10 sixths is 5/3, 1 2/3. Yeah. So is it bigger than 2 or less than 2? I'm sorry.
Less than 2, 1%.
The actual total value, or
Yeah, after you take the 6, yeah. After you divide the 6.
after you divide? So is it in here is what I'm wondering, or is it over there? Okay, it's bigger than, it's in here? Okay. And then see, there's a distance here. See that radical, folks? You're adding to 5/6, you're adding some amount to get over here. And then symmetrically, you're going to subtract that amount to get over to the other 0. Now, the way I can observe if this is indeed far to the left over here, which it is I could go back to the original, which is on the other board, and the original form was down at -7. So the y-intercept was real easy to see. It's at 0, -7 from the original equation that we had. And so the parabola then comes down and sweeps back up like that. All right, in the interest of time today, I want to make sure I get to the data set. If I did this, and I'll do this I think in maybe the next class session Friday, is if I did this in general, folks, let me show you what it's going to be. If I complete the square on this, and like I said, we'll do this probably in the next class session. If I complete the square on this in general, I'm going to end up getting a form like this. Plus some value. Now, I don't remember off the top of my head what that is. So I'm just going to call that K for this moment. Actually, I think the book did this for us. And I can get it up here just for completeness. Just give me a second here. Four AC minus B squared over 4A. There we go. And the way this is oftentimes written in general is this way. Like this. And what you're familiar with is if this happens to be a sketch of roughly of a general one, then how could I label this point right here where my finger is? Look at the original. 0 for x, C, right? 0C. And I could label this vertex at HK, couldn't I? Vertex at HK. And H would be actually, I think that should be a plus sign right there. Yep. So this x reading then is really minus b over 2a. No. H would equal minus b over 2a. H would equal minus b over 2a. So x minus a minus right there. Okay. So let's leave that general form for now and come back. But what I wanted to point out to you is this is the completed square format where you can just look at this as we did in these two examples earlier and identify where the vertex is, H and K. And the y-intercept's easy. Yeah?
If you know, like in 95, they'd have you find negative b over 2a, just plug it into the formula.
Yes. Yeah, we can do that as well. Yeah. Now, let's, in the interest of time, I've only got about 5 minutes or so left. I'd like to do a quick data problem with you that is quadratic in character. So I'm going to do this rapidly since I did one yesterday with you. And what we'll do is go to the computer screen up here. And I'm going to pick a problem out of, and you don't have to punch along with me. All you could have to do is take some notes. Let's say, I think I can do this quickly. I'm going to go to Stat. I'm going to clear my list. And I'm going to clear L1 and L2. So I did that. Then I'm going to go to Stat, Edit. And what I'm going to do is pick a problem like number 28 on page 162. Here's the data set. I'm just going to read it off as I do it. 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200. Now I'm going to go over to my second data set, L2, and I'm going to enter the data. 25, 40, 55, 65, 71, 77, 77. Notice the same output values there. 75, 71, and 64. As I mentioned yesterday, you have to make sure that you have the same number of elements in each list. Next step is I go to Stat. Actually, what I want to do is I want to set a viewing window. And so I look at my data set, and I can see I have X data from 20 to 200. So I'm going to go minus 20 to 220 and put tick marks every 20. And then vertically, I range from 25 to 77. So I'm going to go minus 10 to 90 and put tick marks every 10. Now I go to Y equals, and notice I have turned on stat plot. The way I normally would do that is I would go shift on my Y equals key, and I would go to number 1 here to turn on stat plot. I would make sure that I hit enter on that. I then come down and make sure I hit enter on this for a scatter diagram, and then I come down here and make sure this is L1's label and L2's label, and then I hit graph. Here comes the graph. Looks very nicely like quadratic data, doesn't it? Okay, next step is to now fit a quadratic regression curve through there. So I go stat over to the right to calculate, and I look down here and I pick item number 5 for quadratic regression, and I hit enter, and it comes up with an equation, y equals ax squared plus bx plus c, and then on paper I would normally write down these numbers to several decimal places on paper. I want to now take that equation and store it here in the calculator. So I go to my y equals screen. I'm sitting right here. I then go to, anybody remember from yesterday? I now go to variables, VARS, and I pick item number 5 for statistics, and then I come over to the right to where the equations are, and I hit number 1, and watch what happens. This regression equation, number 1, is automatically, with all its detail, now stuffed into the calculator. I then hit graph, and this is a really nice looking curve fit. So we now have that mathematical model that fits the data quite well, and as I said yesterday, we could go in between data points in here. And what if I was interested in, this happened to be the height of a ball when you throw a shot put, the height of the ball versus the distance, the height of the ball versus the distance. So if I turned on trace and then I down arrow onto the actual regression curve, I could go to, say, 35, and I could see, you can see I'm in between the data points, and I actually could get a reading, 35. The height would be approximately 37.2 feet. So for those who are looking in the book at this problem, this is a model of real data, number 28 on page 162. Okay, so that was a pretty quick and dirty quadratic function session today. All right, so that'll end it for today. And we'll see you in the lab, the computer lab, tomorrow morning by 10 o'clock, and we'll do the midterm there.